Part 2. So last time we focused on the 3 ways triangles can be similar. Those shortcuts are, let's put them at the top, angle, angle, similarity, side angle, side similarity, and side, side, side similarity. Now we're going to focus specifically on right triangles and how right triangles, using angle, angle, similarity, how we can get some very special relationships just in right triangles. This relationship happens when you start with a right triangle. So here we have right triangle, BAD. And then we draw in the altitude, just trace that with me, corner to a right angle. And then from this, we created with that altitude 2 additional triangles. Triangle BCA and triangle ATC. And if you look carefully, first off, let's put our right angles where they belong. All 3 triangles have right angles. Now looking at the original triangle, BAD to the blue, they both share this angle right here. So they both have a right angle and they share that angle, which makes that blue triangle and the red triangle similar. And remember, the minute you have similar triangles, you're going to have proportional relationships. That's important. The implication of similarity is ratios equal. Now from the red to the green, once again, they both have a right angle. And they both share this B angle, which makes the red to the green also similar. And the property for both of these is angle, angle similarity. So the original red triangle, when you draw the altitude, creates 2 triangles which are similar to the original. Now, because of these interplay of similar triangles, we have these 3 specific proportions. So now we're going to label this triangle in a very specific way. We have our altitude. So here's your original right angle. There's your right angle with the altitude. Then in this right triangle, we have the long leg. Excuse me, the short leg, the long leg, and of course the hypotenuse. Then there's 2 additional pieces of the hypotenuse you need to watch out for, and that is what's called the long segment, which is the piece of the hypotenuse that's split underneath the long leg and the altitude, and then the short segment. Okay, there are 3 proportions you need to be familiar with. One of them deals with the short leg. Now be very careful. I'm going to use SL for short leg. Look where I put it. And you have the long leg. I'm going to use LL for long leg. And then altitude. Notice the position I put all of these in. In a proportion, this particular position is called the geometric mean. This particular position is called the geometric mean. So in this scenario, the short leg is the geometric mean between the short segment and the hypotenuse. The long leg is the geometric mean between the long segment and the hypotenuse. Notice those are almost exactly the same, except one is dealing with the short leg and the short segment. The other was dealing with the long leg and the long segment. Then the altitude is the geometric mean between the short segment and the long segment. So let's just trace this out. Let's trace out the first one. See the little finger there? Trace with me and say it. Short segment over short leg equals short leg over hypo. See the little finger? Follow and say that one more time. Short segment over short leg equals short leg over hypo. Let's do the long segment. Long segment over long leg equals long leg over hypo. Do this last one. Short segment over altitude equals altitude over long segment. You need to have these memorized. So you might want to trace that a few more times. You need to. Now you can use this to give another proof of the Pythagorean theorem. Taking a look up here, notice what we labeled. This is C is the hypo, so what we're using here is the A for A squared and B for B squared and C for C squared. So because of this, all three of these triangles, remember there's three triangles, the larger triangle, the left and the right, created by the altitude, are going to be proportional. Which means one of the things you can do is this one right here. You can flip it around. You can go hypo over the long leg equals the long leg over the long segment. That's one. And then we can go like this. We can say A over B also equals Y over H. And another one that's true is C over B equals B over X. That's the backwards of the short segment over short leg equals short leg over hypo. Now if you cross multiply here, let's look at what we have. We can say C times Y equals A squared. Notice what I did there. Very careful. This one, B squared equals C times X. So addition property, we can do A squared plus B squared equals CY plus CX. And if you do backwards distributive, C equals Y plus X back to the original, but Y plus X already equals C, so that equals C squared. Therefore, final, A squared plus B squared equals C squared. That is a proof using similar right triangles. So for this page, you're going to work through using the three proportions right here. We'll get you set up for the first one. So see these three proportions right here? That's what you're going to use on this page. Let me give you a suggestion on what I'm looking for. So let's label what we have here. We have ourselves a short segment, altitude, and a long segment. And we know that the altitude is the geometric mean between the short segment and the long segment. Therefore, right here, let's circle plug check. Our short segment is 3. Our altitude is 4. Altitude 4. Long segment is Z. We cross multiply. 3Z equals 4 squared. 3Z equals 16. Therefore, Z equals 16 over 3. Leave it exactly like that. That's called exact term. Exact terms. No decimals. Exact terms means fractions and or simplified square roots. Finish the page and check on the board.